Look at something rather nasty now, which sort of frightens people, the Arrhenius equation. But before we do that, I suppose we better start trying to understand what's going on. So it's all about reactions. We've got a reaction, and for something to work, we've got to have a collision occurring. Now, that's just not good enough. And in chemistry we need more, and we find that basically if we try and get things to work, they don't quite work out right, and the reason is because of various things. Let's have a think about some of these. I've got then simply molecule A, and this is going to collide with molecule B. Right, so what do we need for a reaction to take place? Well, it's pretty obvious that, number one, they actually have to collide. But when they collide, the answer is they only may react. Not will, but they may react. It isn't enough for the two molecules here to collide. They have to collide the right way round. They have to collide with enough energy to break bonds, and the chance of this happening is sort of, fairly remote. If you want perhaps three molecules to react, then here the chances are going to be less. All three particles have got to arrive at exactly the same point at the same time. Everything's got to be lined up right, and they've got to have enough energy to react. And basically, well, that's not going to happen very often, is it? Fortunately, in fact, for us, we've got an awful lot of molecules. It depends what we've got. Let's suppose we take some chemical like ethene. And having got something like ethene, I'm going to react hydrogen chloride with it. Well, they're going to react, they're going to form chloroethane. But what happens if they react in the wrong direction? Well, simply nothing's going to happen. So this reaction's only going to happen if the hydrogen end here approaches the carbon-carbon double bond. If there's any other collision, it's not going to work. The two are simply going to bounce off of one another. So, of the different collisions, these aren't going to work. If it comes in with chlorine first, then again, that's not going to work. It's only going to work if it comes in that direction at the right speed. So here we've got any type of collision with unsymmetrical species. You're going to expect them to sort of not necessarily work properly all the time. And basically, even if these species are orientated properly, you're not going to get a reaction unless they collide with the minimum amount of energy, and that we call the activation energy. And you're probably familiar with a graph such as this one, where we've got our reactants. Let's have our products down here, and it just doesn't go from our reactants to our products, but instead we've got to provide this extra energy, the so-called energy of activation or activation energy. And that's basically here a simple profile here for something that is perhaps an exothermic reaction. If the particles collide with less energy than this activation energy, then nothing basically happens. They bounce apart. If you want, you can think of this activation energy as perhaps a sort of a barrier. You've got to get above this activation energy if you want things to work. Any chemical reaction always consists of, first of all, breaking bonds and then making bonds. The breaking of bonds, we need energy. And the making of bonds basically here releases energy. And if we start looking at this, we can see where if these collisions are relatively gentle, then there's not going to be enough sort of energy here to start this bond breaking process. So this is where we meet the Maxwell-Boltzmann distribution. Now, let's see this for a particular gas. If we look at basically the number of particles, and we look at here the energy, then if we just look at some ordinary gas at any time, then generally most of them are going to be fairly low. And we're going to have most of the particles with fairly low energy, and we're going to have fewer particles with very high energy. We're going to have very few down here, very few here, and most of our particles are going to have this amount of energy. This basically only applies to gases, but really we can think about this applying to liquids as well. Let's put a line in here. This here is our energy of activation, and only the molecules with this much energy or more are basically going to react. Does it mean, of course, that they can never react? Well, no, of course it doesn't. There are all sorts of exchanges of energy between particles all the time. Some speed up, some slow down when they collide. And what happens if we change the temperature? Well, if we change the temperature, then this graph may have its shape changed so that more molecules here have the required energy basically to react. So that's Boltzmann. Now let's try and look at an experiment. So I've had a go at doing a little experiment, and what I've done is I've taken here my colorimeter and I've taken some sodium thiosulfate and some acid, and what I've done is I mix them here in this little cuvette. This is one made by Pasco, and what we do is we set these at different temperatures. They're at temperature, I put them in here, and what we do is we start to record the reaction, and here you can see my results for different reactions. What I've got is a whole series of different reactions. We did this one at 5 degrees C, and you can see that this one took basically forever to work. And then we did this at 15 degrees C, was faster, 25, 35 and 40. Now, I didn't get nice temperatures out of this. Well, why not? Well, I have a problem with this little device. And the problem I've got with this little device is I can set these things in a water bath at the right temperature. But when I put them in here, they do start to cool down. And trying to keep this hot or cold is remarkably difficult for me to do. So I need better equipment so I can actually record this. But within the realms of what I've got, then I've managed to get some reasonable data. So let's see what I can do with that data. We've got then this data, and what I can do is I can work out the gradient, the slope of the fastest reaction. So the rate at it was the fastest, I can record this data. And what I've done is I've taken this data and I've put this into a spreadsheet. And I've plotted this data from my spreadsheet. So I've got, first of all, my temperatures, I've got my rates, and you can see here it's approximately following a curve, but some of my data is not terribly spot on. So I've got an idea here. This is plotting rate along this side, and I've got my temperature along the bottom axis. So I've got sort of a curve. Now let's see if we can try and understand what goes on with this curve and what we can actually do to calculate various bits and pieces with this. And this is where we come in to meet the Arrhenius equation. Now, the Arrhenius equation was sort of designed to try and fit in with some sort of common knowledge. So we've got this thing, we have plotted the data, and now what we can do is let's see if we can take this and make some sense of it. Right, so starting off, then let's meet the Arrhenius equation. Think about it. Common knowledge, I suppose, that reactions occur more rapidly at higher temperatures. So we can think of the higher the temperature, then we can think really that we've got the faster the reaction. And that is what we're seeing in this data that we've pulled in, and we can see when we look at the graph, which is sort of desperately going up, something like that. Now, the reasons aren't that hard to understand. Thermal energy relates to the motion of the molecules. As the temperature rises, then we can see that the molecules move faster. And we're happy with that. They would probably collide more vigorously. There is probably, if there's more collisions, there's more chances of getting the right orientation. I'm not saying that the orientation here is going to change. There are going to be just as many bad collisions as good ones. But if we've got more collisions, then this is more likely to happen. And it doesn't matter what sort of ideas you come up with. Most people agree with this. So by about, in history, I suppose about 1890, this was quite common knowledge that high temperatures speed up reactions, and we'd often found that you get a doubling of the rates with every sort of about 10 degrees Celsius rise. But why? Well, it was around about 1899 that a Swedish chemist called savant Arrhenius came up with some ideas. He combined this idea of activation energy and this Boltzmann distribution that we've come across, and he put it into a nice, very simple, friendly equation that our rate here is going to be some, it's called the Pre-Exponential Factor. Now, to a certain extent, this is more what I'd like to think of as a fiddle factor. This is something that actually changes what we observe with what the theory ought to be. And I'll explain more about that in a minute. We get E. This is our natural logarithm, and it's raised to the power of the activation energy over the gas constant and times the temperature, which gives us our average kinetic energy. And if we think about this but neglect A for the time being, we can see that this can make a little bit of sense. Now, as we go along here, let's just try to sort of think about what we're seeing. This is, if you like, another form of the exponential decay law that we've seen before. So it's something working like that. Now let's look at some other bits. Let's look at RT. RT here is our average kinetic energy. And this is very similar to what we've looked at in the Boltzmann. And we've also got here something to do with the activation energy. We've got to have a relationship between the activation energy and the average kinetic energy. The larger this ratio, the smaller the rate. Hence we're going to have a negative sign. This means that the higher the temperature and a low activation energy will favour a large rate constant, and it will therefore speed up the reaction. And because this is now as an exponent, then a little change in this is going to have a substantial change on the reactions. So let's have a look at a sort of reaction, and let's see if we can have a look at this working. So I've got a graph here, and we're going to plot e to the minus EA over RT here, and I'm going to plot that here against my energy of activation, and we get a real mess until we decide that what we might try to do is give ourselves a log plot on this side, and then what we get might be a graph that will look something like this. I'll do it in a couple of colours, which might make it a bit easier to see. So let's plot this at perhaps 0 degrees C, 0 Celsius, and if we do it hotter, perhaps at 100 degrees Celsius. And we're seeing here nice straight lines. Why are we seeing nice straight lines rather than curves? By putting things into logs, they tend to make nicer straight lines. So let's look at a rate of reaction. What is a rate of reaction? So we know from a rate of reaction that the rate here is going to equal some sort of rate constant, and we've got here the concentration of a chemical, and we might have here an order of this reaction that we looked at in the previous video to the other one. So there's our rate equation, and that shows the effect of changing concentrations. What about all the other things like temperature and catalysts? What do they do? And that is why we need this. I have to think how to spell his name. Why we need the Arrhenius equation. So this here works well for concentration, but we need to try and work out these other bits and pieces to try and work out what we've got. So in this Arrhenius equation, simply we've got to worry about the energy of activation, we've got to worry about the gas constant, and we've got something here about temperature. Now, the reason I've gone back here is to say that temperature is measured in Kelvin. Just the way life is, I suppose. The gas constant R comes from this thing about pressure and volume, number of moles, and the gas constant and temperature, which is relating pressure and volume and temperature, and this thing comes up in all sorts of chemistry. The activation energy then we've met in Boltzmann. It's the minimum energy required. Here, the minimum amount of energy required for the reaction to occur, and this is expressed in joules per mole, not kilojoules per mole. Now, E always causes mathematicians and all sorts of people problems. We have to think about E. This is basically the natural logarithm, and this is what nature uses. When we played with logs, we started off logs to make multiplication easier, because when I started this, calculators hadn't been invented. Oh no, I had to use log tables and worse slide rules. And we use logs, which use these things. Log to the base 10. Why do we use log to the base 10? Simply because we've got 10 fingers, thumbs. But nature doesn't have 10 fingers and thumbs, so nature chose a completely different number. And this number, if you do maths, you might have some idea about it. And if you don't do maths, don't care about it. It's just a number. And it's a number which is 2.718. It's a mathematical number. It's like pi, this number. It is just an irrational number, and you'll find it if you're looking on your calculator. We find we've got this little thing here. There it is, e to the something. So we meet this to try and play with it. And then we've got this a, which I'm desperately trying to ignore. A is sometimes called the pre-exponential factor. Other places we call it the frequency factor. And I've said it's basically a fiddle factor. It's a term which includes all the factors like the frequency of collisions, the orientation, and this does vary little bit with temperature, but not a lot. So if we're looking at a small temperature range, and that's certainly what I was looking at with my experiment, then this is assumed to be sort of a constant. Now, this Arrhenius equation, K equals a e to the power of minus EA over RT, can be looked at in a different way. I can basically do logs of each side, that gets rid of this horrible thing, and I get the natural log of k equals the natural log of A minus the activation energy over the gas constant times the temperature in Kelvin. There we are. So we can use this Arrhenius equation to show the effect of the change of temperature on the rate constant, and therefore basically on the rate of the reaction. If the rate doubles, for example, you'll also see the rate of reaction will increase. So what happens if you increase the temperature from, maybe let's go from 10 Celsius up to 20 Celsius? Well, we have to work in Kelvin, so we're going to go from 293 Kelvin up to 303 Kelvin. Notice there's no degrees. Kelvin is an absolute scale. This frequency factor is going to be more or less constant. So we only need to really look how this energy of activation is going to change in respect to the gas constant and this temperature. Now we've got to try and do some maths now. I suppose I was talking to my son, he's a chemist, and he described basically the Arrhenius equation is basically chemists trying to play maths, and it didn't work, and so they had to come up with this frequency factor, this pre-exponential factor, this little fiddle factor to try and get something to work. So let's look at a reaction. So let's suppose we've got something, and we'll choose at basically, let's go and choose I'm just thinking I've done that wrong. 10 degrees Celsius is going to be 283 Kelvin, and that's going to be 293 Kelvin. Oh dear, made a silly mistake there. Right, so at something like 20 centigrade, which we're going to call here 293 Kelvin, then the value of my fraction, my e to the minus ea over RT, we get by looking at some information. So if I've got my activation energy, let's make a number up. Let's suppose that's 50 kilojoules per mole. Now that means that I've got to put that in joules per mole, so that's going to become here 50,000 over my gas constant, which is 8.314, times my temperature, which is 293 Kelvin. And what I need to do is work that one out. So let's do that. So we've got my number of 50,000 over my gas constant 8.314 times my temperature, which is 293 Kelvin, and that gives me an answer here of 20.525. Now there is my number here, and we've got here, by raising the temperature just a little bit, we can see that we might get a significant change. So if I increase this to, let's say, 30 centigrade, Celsius is going to give me here 303 Kelvin, and so we're going to get my 50,000 divided by my 8.314 times now 303. I'm not worrying about the minus at the moment. I'm not doing my exponential either at the moment. We'll come to do that in a sec. So let's now, I'm just going to make sure I store that value because I want that one in a minute. Let's look at what else we've got. We've got 50,000 this time over 8.314 times this factor of 303, and we'll see that that's taken it down to 19.84. So let's try looking at what my exponentials are going to be. This is going to be e to the minus that, and this is going to be e to the minus that. Let's see what changes this is going to make. Go back to my calculator, and what I'm just going to do is I'm going to store that number, and I'm going to store that one in B. Right, let's cancel. So I'm going to do my e, shift e to the power of minus, and then I'm going to recall my first number, which was a, and that gives me here 1.21 times 10 to the minus 9. 1.21 times 10 to the minus 9. Now let's try that one again, but this time we're going to try it with the other number. So again, we're going to do shift e, right, we'll do that one again, shift e to the minus, and then I'm going to recall memory B, and this gives me 2.39 times 10 to the minus 9. And you can see there really a 10-degree change in temperature. We've got basically a doubling of the rate of this reaction. So our idea that's observed in about 1890, that 10-degree rise gives a double in the rate of the reaction, does certainly appear to be true. How about a catalyst? What does a catalyst do? Catalysts are really easy. If you remember, a catalyst is something that basically takes part in a reaction, but at the end you end up with what you started with. So a catalyst is basically reducing the energy of activation. So we've got here with a catalyst, the energy of activation is going to be reduced. So let's suppose in this reaction, this same theoretical reaction, my energy of activation is, we said, 50 kilojoules per mole, and when we put in our catalyst, our activation energy will maybe drop to 10 kilojoules per mole. Well, let's stick this into our equation where we've got EA over RT, and I know it's all to the power of e to the minus that. I'm just going to work this bit out just to start with. So that's going to give me 10,000 divided by my 8.314 times the temperature of our reaction. Let's take the original reaction that we had, which was taking place at 293 Kelvin. Let's go and work this one out. And if we do this one, then simply working this out, we'll get something like 10,000 over my 8.314 times by my 293. That's going to give me 4.1, and what I'm going to do is I'm going to store that in memory C. Let's now work out what that is with my E. So I'm going to just work this one out. So we do shift here to the minus, and then I'm going to recall memory C here, and this gives me a value of 0.0164. And if we work out what this is a phenomenal change, in that when we did the reaction up here, we got our values of 1.21 times 10 to the minus 9, and we're down here to 1.64 times 10 to the minus 2, and that is an enormous change in our Arrhenius equation. Basically, with the catalyst here, we're basically seeing a fantastic amount of more molecules that can react when the catalyst is there. So the catalyst really does speed up this reaction. So that gives us some idea how this is sort of relating. Right, so how could you perhaps determine the activation energy? it's quite happy for people to go around saying, yes, we've got this activation energy, but how on earth do we try to determine it? Well, basically, if we try and plot this, we get a little bit more sense of what we're doing. What we've got is, if I draw my graph to sort of remind you of what's going on, what I've got is a graph of 1 over temperature, and we can work out what ln K is. To remind you, we've got ln K is going to equal ln A plus, I was just trying to think here what it's going to be, and it's going to be the minus the activation energy over RT. So if we look at one of these reactions and we start plotting the data that we get, because we can split this equation up if we want to say ln K is ln A plus our energy of activation over R times 1 over T. And then by splitting this up, we can see that we've got an equation here that is Y equals some equation like mx plus c. This is our x, this is our m, and this is our constant. That means that for here, our gradient is simply going to be minus the activation energy over the gas constant. And the gas constant we know, so working out our energy of activation now has become possible. If you're of any interest, where this line intercepts with the y-axis, that is our value here of A. In fact, in this case, ln of A, our fiddle factor to help us try and work out what's going on. So the Arrhenius equation tells us that the temperature and the rate constant are related exponentially. As the temperature increases, so this rate constant K increases. Can we do some of these equations without doing the graph? Yeah. It depends how good your maths is, really. If you're a chemist, I'd stick to using the graphs if I were you. If you're quite good at A-level maths and you've got further maths also in the bag, then yeah, I wouldn't worry at all about trying to work this out mathematically. Basically, as I said, this is trying to work out what goes on, and I've tried to make it a little bit simpler for you to try and give you some idea about what's going on. This pre-exponential factor, this A, is basically something that's really horrible. It's basically just designed to try and fiddle the observed with the expected, and as long as you accept that this is some sort of factor about how often they're going to collide and in which orientation they're going to collide, then that's all you really need to take away about what is A. Too many people worry about A and they want to know what it exactly is, whereas it's sort of something just to be put aside and not worried about too much, because as you've seen in the calculations I've done, basically we've shown that a 10-degree rise seems to double the rate, so we've got some important bits and pieces there. If you found this useful, then please give us a thumbs up and subscribe, and I hope to see you again next time when we do some more A-level chemistry, topic by topic. Until then, stay safe and take care. Bye bye.